Today, our spotlight is on Dr. Douglas Jesseph, a researcher in the philosophy department at the University of South Florida. We chose Dr. Jesseph because his merging of the seemingly unrelated fields of philosophy and mathematics shows extraordinary potential in developing new areas of research.
Today we're here with Dr. Douglas M. Jesseph to discuss the matters of his research in philosophy. Dr. Jesseph is an alumni from Macalester College and received his PhD from Princeton University. He is a renowned mind in both the fields of philosophy and mathematics, and has spent many years researching both. Welcome, Dr. Jesseph, and thank you for being with us here today.
My pleasure.
So before we get into the hard stuff, perhaps you could just tell us a little bit about yourself. Where you're from.
Where I'm from, I grew up in, I was actually born in Colorado and spent my formative years in Wyoming, of all places. But from the age of about 8, I lived in Minnesota. I was went to high school and college in Minnesota. Then traveled in Germany. I had a Fulbright grant first year after college, and then I went to graduate school in scenic New Jersey, where I met my wife at Princeton. And since then, we've moved around a little bit. I've taught at Virginia Tech. I've taught in Chicago at the Illinois Institute of Technology, and 1 year visiting at the University of Chicago. And then North Carolina State University, where I was for 15 or 16 years. And since 2008, I've been here at USF.
Interesting, very interesting. So, Dr. Jesseph, tell us about your area of expertise.
My research focuses on philosophy of mathematics in the 17th and 18th century, which is to say that I'm interested in the historical development of certain kinds of mathematical theories, but also philosophical concerns that are raised by those kinds of theories. So specifically, if you look at the mathematics from, say, 1600 and compare it to mathematics that's done in, say, 1675, it's almost completely unrecognizable. I mean, it's just a radical change. In 1600, the standard way for someone, a professional mathematician, if there was such a thing, the standard employment would have been to be preparing editions and translations of Greek authors. And the assumption was essentially that the Greeks had achieved pretty much everything that one could achieve mathematically. The idea would be simply to put everything in sort of a nice, tidy package. By 1675, the influence of the Greeks has waned rather dramatically, and you have new methods, in particular analytical geometry, famous from Descartes, which you may remember, Cartesian coordinates and all that kind of stuff, and also the development of infinitesimal methods, which turned into the calculus in the 1670s, 1680s. Those radical developments actually raise some very interesting philosophical questions. In particular, mathematics has always been philosophically kind of interesting, because it seems that mathematical truths, when we know them, or when we can demonstrate them, they're known in a more industrial strength way than ordinary sort of facts about the size of the universe, or how many planets there are, or how tall is the Eiffel Tower. Sort of empirical questions like that seem rather different than mathematical questions. Mathematical truths are necessary in some sense, that the world couldn't be in such a way as to make 17 not a prime number. But it also, the new methods raise some very interesting questions about what counts as a proper demonstration. If you look at the development of algebra, for example, you may be sort of puzzled by this thought that, you have all of these algebraic equations, you introduce these nifty little symbols and rules for manipulating various symbols, but how do you know that what you're doing, dividing or adding or subtracting or taking roots and whatnot with all of these sort of formal manipulations of algebraic symbols, what reason do you have for believing that corresponds to anything in the actual world? And how is it that a series of algebraic manipulations can tell you something about the behavior of a curve, say, or give you some information about the nature of some geometrical objects? And that raised all kinds of interesting questions. Further, with the development of infinitesimal mathematics, the calculus, it was sort of standard procedure, more or less, for mathematicians to say, well, we're interested in the behavior of a curve at a point, so we'll look at an infinitely small increment in the neighborhood of the point. But what's an infinitesimal? Well, it's a quantity that's greater than nothing, but it's less than any finite real number. So it's greater than 0, but less than 1, less than 1/2, 1/4, 1/8. It sort of hovers between something and nothing. I mean, it's a very, very weird kind of thing. And of course, there's the concern that these sorts of things are not rigorous. And so a lot of my research is involved in sort of looking at debates about how the calculus was founded, looking at debates about the status of algebra or algebraic equations. And as luck would have it, if you make a list of the great mathematicians and philosophers of the 17th century, they all sort of overlap. Descartes, fundamental contributions to mathematics, but also one of the great philosophers, Leibniz, for example, Pascal, Berkeley in the 18th century. So these are the sorts of people that I ponder. That's the main focus of what I'm doing these days.
Interesting. So would you say that your ventures into mathematics have caused you to venture deeper into the world of philosophy?
Yeah, I mean, I suppose. I mean, I've always been interested in sort of philosophical questions raised by mathematics. I was a mathematics major and philosophy major as an undergraduate. My first research out of college, I had a grant to go to Germany, and I was interested in the work of a 19th century philosopher, logician by the name of Gottlob Frege. And I was working on Frege, very serious German philosopher. And Frege had this unfortunate event that befell him. He worked out this enormously complex and very interesting system, the foundations of all of mathematics. But what he didn't realize was that the theory that he was basing it on, the theory of sets that he was using, turns out to be pathologically inconsistent. And this is a bad thing. You can show that the theory of sets, the set theory that he was using, in fact, yields contradictions. And therefore Frege, I mean, this was just as his magnum opus was being published. And he continued, tried various and sundry ways of trying to repair the damage. But I was interested in his way of thinking about the real numbers, and to a lesser degree, the way that his theory could be applied in constructing elements of the calculus. And what I noticed in reading Frege and doing some research on his system was that he spent a lot of time attacking the views that had come earlier. Like most philosophers, he thinks that the history of philosophy is a series of errors made on the way to my view. This is standard operating procedure. But as I was reading it, I discovered that I thought the people that came before Frege were more interesting. I mean, he was mentioning Newton and Gauss, but also Leibniz and other kinds of characters. And so I ended up, by the time my grant was over, I decided, Frege is not that interesting. I'm interested in sort of 18th century disputes on the calculus. And that's sort of how I got started.
Could you tell us a little bit about your research, the various philosophers or mathematicians that you've done?
I started out working on George Berkeley, who is known he's an 18th century philosopher. He's known for the radical thesis that there are no material objects, that the world consists entirely of minds and ideas. That I find preposterous. But he also wrote in 1734 a very, very interesting little treatise called The Analyst, which was an attack on the foundations of the calculus. And what motivated him to do it was an incident where some noted London doctor was on his deathbed, and someone came to visit him and said, "Well, hope you've gotten right with God, and last rites and all that." And the doctor said, "Oh, I have no worry about that, all that nonsense. The great Edmund Halley, who deals so much in demonstration, has assured me that religion is an imposture, and therefore I have no use for it." And Berkeley thought, well, this is a problem. Because he wanted to defend the true Anglican faith against all of these atheists and infidels. And so the point of The Analyst was to show that a mathematician such as Halley, who believes in the calculus and yet derides the mysteries of religion, is in fact being inconsistent. And so he showed very carefully and very, very cleverly that the foundations of the calculus as used by Newton and by Leibniz were actually, if not inconsistent, breathtakingly close to inconsistency. Because what happens, this is something they never tell undergraduates who are taking mathematics classes. I mean, they teach you the calculus and they tell you about the epsilon delta continuity definitions, how to take limits and all of that. And that's all highly sanitized. Back in the day, in the 1680s or in the early 1700s, when people were dealing with issues in the calculus, they would simply allow infinitesimal increments. You consider a function, f of x equals whatever, then you look at f of x plus dx. Dx is understood as an infinitely small piece of whatever the x-axis happens to be. Substitute that into the equation, expand, diddle around, take some simplifications, do some algebraic manipulations, and then divide typically by dx, therefore treating dx as something greater than 0. And then at the end of the day, when you have these leftover terms in dx, you just discard them as equal to 0. So you're on the one hand treating it, the infinitesimal as greater than 0 when you need to divide, and equal to 0 when you need to cancel terms. Berkeley pointed out that's actually inconsistent. And therefore, he raised these objections against Newton, to a lesser extent against Leibniz. And interestingly, what happened is that the whole business blew up. There was a huge dispute among British mathematicians from the 1730s to the 1760s about how best to respond to Berkeley. So that's where I got started. And then I ended up I've been working for a number of years on the mathematics of Thomas Hobbes, of all people, whom you may have heard of as a 17th century political philosopher. But Hobbes also thought that he was a great mathematician. In this respect, Hobbes was wrong. He thought that he could square the circle, give arbitrary angular sections, and solve all the great outstanding problems of geometry. But what he came up with was the character of his mathematical work is pretty minimal. But he does have an interesting ontology of mathematics. Hobbes was a materialist. He believed the only things that exist are material bodies moving in space. And if that's all you've got to work with, then you have to ask the question, well, what about mathematics? What can you say about the number 11? Is it a material body? That seems hopeless. And what about geometry? Geometry we typically think of as dealing with some kind of abstract objects, right? Perfect spheres that are not to be found in nature. And Hobbes decided the only thing to be done was to take geometry as a science of physical bodies. And so on Hobbes' view, a point is actually a body, but a body sufficiently small that its magnitude can be neglected, which is the physicist's definition of a particle these days. So I started working on Hobbes and got interested, and Hobbes spent the last 25 years of his career in this gigantic dispute with a mathematician by the name of John Wallis. And so I wrote a book on that, and I've been working steadily on trying to get some of Hobbes' mathematical and philosophical writings together in a proper edition. So that's most of what I've been doing.
In your time here at USF, have you focused more on your interest in mathematics or in your interest in philosophy, or has there been sort of like a meld of both?
Probably a little bit of both, with a sort of 60-40 or 65-35, the philosophy over the mathematics. I've been looking into sort of historical development of various kinds of philosophical theories, and in most of what I do then is sort of try and figure out how all of these historical actors sort of connect up with one another, who's reading what and whom, and what are the sort of standards of debate. I mean, what sorts of things do they take to be uncontroversial, and what sorts of things do they regard as standing in need of proof? And then I sort of work through those conceptual issues. This has led me to sort of side interest that I have in 17th century natural theology, arguments about the existence of God, things of that nature. So I end up reading, when you start reading Hobbes and Spinoza, you end up in sort of theological territory fairly quickly. And on my interpretation, Hobbes was an atheist who denied, in fact, the existence of God, which makes him something of an outlier. I mean, most 17th century philosophers were card-carrying Christians of one stripe or another. So that I've been dealing with those sorts of issues for the last few years.
Interesting. And how do you feel that your research has affected other fields of study?
That's very difficult to say when you do philosophy, right? I mean, you put stuff out there, people read it, and you say, well, there you are. I've certainly, some of my works attracted a fair amount of attention from, of all things, historians who are interested in sort of intellectual history. And one of the things that I've been able to convince a fair number of people is that if you're doing intellectual history of a character such as Thomas Hobbes, about whom an enormous amount has been written, you really don't get a complete picture unless you try and connect Hobbes' views of method up with the mathematics of his day. And so in part what I've been a fair amount of what I've done is had some impact on the way that intellectual historians especially of 17th and early 18th century thought work. I can't say that I've made any, I've contributed to the literature on Hobbes and convinced a fair number of people that Hobbes' mathematics, although grotesquely mistaken in some parts is also interesting in certain kinds of ways. Some interesting methodological and mathematical doctrines are developed by Hobbes. And again, his historical context is quite interesting. When Hobbes was born in 1596, that was at the time when mathematics was essentially focused on the ancients. He lived all the way to 1679, and really surpassed significantly. Sort of outlived the old mathematics that he grew up with. So he actually lived through this significant revolution in mathematics. And so I've been able to convince a fair number of historians of mathematics that reading Hobbes is not a complete and utter failure, waste of time and mistake.
In this next section, Dr. Jesseph talks about his outlook on mathematics. We focus on the method by which researchers in the field of mathematics develop their ideas. We think you'll also see how Dr. Jesseph ties mathematics to philosophy as he discusses some of the epistemological issues regarding the reality of numbers.
An important aspect of math is the very high standard of rigor that we hold mathematical proofs to. Why is it that we can appear to know things that are universally true in mathematics?
Excellent question, and one that has really puzzled people down the years. The basic idea would be something like this, that a mathematical demonstration, when rigorous, will begin with first principles, definitions, and axioms, let us say. And then we'll help ourselves to some logic. Let's not get too worried about what kind of logic, enough to do the job. First order quantified logic with identity, say, which is a nice, concise chunk of logic. And then a rigorous demonstration would be one that begins with these transparently true first principles. 0 is a number. Every number has a successor. No two distinct numbers have the same successor.